Today on AI Paper Slop, we are breaking down dynamic compression in recurrent networks by Jyotish Purdy, Ryan Boldy, and Pulkit Agrawal from MIT's Improbable AI Lab.
Right.
And the core insight for this analysis is straight to the point. Recurrent models, like RNNs or modern linear state space models, compress history into a fixed-size state in a single left-to-right pass.
Yeah, just one pass.
Which means this architecture forces them to compress data before they actually know what future downstream tasks will need from that data. And that inevitably leads to a compromised task-agnostic state.
Exactly.
But the breakthrough introduced in this paper is dynamic compression via selective re-scanning. By keeping a cheap, lossless storage of the raw input tokens, the model can actually predict which pass tokens matter for a highly specific task, selectively reread them, and then revise its fixed-size state on the fly.
It's a massive shift.
Yeah, it trades a marginal amount of extra compute at inference time to massively reduce the required memory capacity, literally slashing the needed recurrent state size by orders of magnitude. So let's unpack this architecture.
Well, to really get why this matters, we have to look at the context-length scaling war we've been fighting for the last few years. It's fundamentally bound by big O notation, and this paper attacks that bottleneck directly.
Right, because transformers require O of t-value memory and attention compute.
Yes. Every single new token you add to the sequence increases the memory footprint and the computational costs linearly, which, that becomes prohibitive in production environments that are bounded by memory bandwidth.
It just doesn't scale infinitely.
No, it doesn't. And that's why recurrent models offer this theoretical holy grail of efficiency, because they require O of one state memory and O of one recurrent compute per token.
But the math for that recurrent update is elegant but incredibly restrictive.
Highly restrictive, yeah.
Because the stated time t, S sub t, is just a function of the stated time t minus 1 and the new token x sub t. So S sub t equals f sub theta of s sub t minus 1 and x sub t. The parameterization, theta, stays fixed. And that single pass formulation is the exact bottleneck the MIT team is addressing. Any future utilization of a token relies entirely on how effectively it was compressed into that S sub t state at the precise moment it was initially read.
And at the precise moment of reading, the model is flying blind regarding future utility.
Yeah, it has no idea what's coming.
Exactly. It builds S sub t before it has any forward-looking context about the future task, which we can denote as tau. To put it in theoretical terms, there is an optimal state, S star sub t of tau, for any given task.
Because different tasks demand entirely different allocations of the finite state capacity.
Yes, exactly. So a mathematical reasoning task might need to preserve the exact numerical values from the beginning of a prompt at incredibly high fidelity.
Right.
While a summarization task might only care about the semantic gist of the middle paragraph.
It essentially forces the model to pack a single generic suitcase for a multi-country trip where the itinerary is completely unknown.
That's a great way to look at it.
Like, you allocate your limited capacity to a generic compromise. So you pack a few layers, some versatile shoes, but you inherently lack the perfect outfit for any specific extreme condition.
Right, you're just averaging everything out.
Yeah, you don't have the heavy parka for the Arctic or the tailored suit for a gala because you simply couldn't afford the state capacity to preserve high-fidelity information for every possible contingency.
And that means the single-pass model is attempting a mathematically impossible balancing act. It is trying to construct a single-state S sub t that somehow supports all possible task-specific optimal states simultaneously.
Which just doesn't work.
No, it doesn't. Once high-fidelity information is discarded to make room for this generic compromise, the information theoretic loss is permanent.
It's just gone.
Completely gone. It cannot be recovered later when a specific query actually demands it.
So to prove this, the researchers designed a highly specific synthetic torture test to quantify exactly when this generic suitcase approach breaks down.
Oh, the torture test is fascinating.
They call it the continual function reuse task. And they forced the model to observe k different random linear functions sequentially within a single context window. These are 8 by 8 matrices, so the dimension d is 8.
And the sequence structure is heavily engineered to isolate this memory limitation. The sequence begins with what they call a basis phase, where the model receives labeled input-output pairs for each of the k functions.
Okay, so it's getting the examples up front.
Right. And crucially, they set the number of pairs b to 16. Because b equals 16 and the dimension d is 8, the linear system is strictly overdetermined.
Meaning the model is given more than enough information to perfectly learn the matrix weights.
Exactly. These tokens are fed into the network as 4 tuples. So you have the input vector, the output vector, a binary flag set to 1 indicating the output is a ground truth label, and a basis identifier.
Okay, so after the basis phase comes the query phase. The model receives a few-shot block of examples that helps it identify which of the K functions it is actually supposed to use. And finally, it receives a query input to solve, and that binary flag is flipped to 0, signaling the model to output the prediction.
And this right here is where the static compression crashes.
Yeah, the numbers on this are wild. When K equals 1, the model solves the task easily with a modest state size of roughly 3,000 state elements.
Which is very standard.
But pushing to K equals 3 forces the required state size to roughly 3.1 million elements to achieve the same loss.
A massive jump.
Wait, going from 1 function to 3 functions requires 1,000 times more memory. Why? Is it because identifying the function takes a different mental resolution than actually doing the math?
It makes perfect sense that scaling to K equals 3 blows up the state capacity like this. Identifying the target function from a few-shot prompt is a low-resolution semantic task.
Right.
But actually doing the matrix multiplication requires holding the exact weights. The model is essentially destroying its own state, trying to keep all K matrices at high fidelity simultaneously.
Just too much high-res data for one pass.
Yes, the catastrophic interference is unavoidable in a single-pass paradigm. It doesn't know which of the 3 functions will be queried, so it attempts to superimpose 3 distinct 8x8 matrices into the working memory at maximum resolution.
All at the same time.
Right. And the parameter space required to isolate and maintain those overlapping high-fidelity representations scales disastrously. Trying to solve continual learning by just linearly expanding the recurrent state dimension is a complete dead end for ML engineering.
Which brings us to the architectural fix. To implement dynamic compression, they utilized a gated DeltaNet architecture.
Yeah.
Specifically, a relatively small setup. We're talking 4 layers, 6 heads, with an embedding dimension of 256.
And the gated DeltaNet is the perfect substrate for this because of how it handles memory updates. It is a linear attention model that maintains a matrix-valued state, and it updates that state using a gated delta rule.
Can you break down that delta rule for us?
Sure. The delta rule essentially computes the difference between a target value and the current state's projection, and it updates the state matrix based on that error.
Ah, okay.
But the critical components for our discussion are the 2 gating mechanisms. There's an alpha gate, which controls global forgetting or exponential decay of the state, and a beta gate.
And that beta gate is the update strength signal.
Exactly.
It dictates on a token-by-token basis how strongly the state matrix should be updated toward the new value at a given key.
Right. It decides how important the new token is to remember.
So to leverage this, the researchers modified the DeltaNet by giving it a 2-head solution at the output layer. There is the standard prediction head that outputs the actual answer to the query, but they also introduced a selection head.
This is the really clever part.
At the end of the few-shot block in the query phase, this selection head outputs a discrete index. It basically acts as a pointer saying, based on this few-shot pattern, the matrix I need to solve the query is located at basis function number 2.
And that selection head index is the trigger for the selective rescan. I want to break down exactly what this looks like mechanically at inference time.
These are.
So the model is decoding tokens standardly, doing its O of 1 state updates. When the selection head fires its index, the system temporarily halts the standard forward generation.
It just pauses.
It pauses. It uses that index to look back into the lossless storage of the raw tokens, pulls the exact block of 21 tokens that define function number 2, that's the B equals 16 pairs plus some overhead, and it routes them through the recurrent cell second time.
So it is actively overwriting the generic compromised state with the high-fidelity weights of the specific matrix it now knows it needs, precisely milliseconds before it has to compute the answer.
Yes. It uses the persistent recurrence of the DeltaNet to aggressively write that specific function back into the matrix-valued state.
Oh, wow.
During this targeted rescan, the beta gate flares up, writing the high-fidelity information with maximum strength because the model now has the forward-looking context it lacked during the first pass.
It finally knows what outfit to pack.
Exactly, and the oracle results validate the theory completely. At K equals 3, where the single-pass model required 3.1 million state elements, the dynamic rescanning model achieves a lower error rate using a state size of just 111,000 elements.
Wow.
Yeah.
Okay, the efficiency gains are undeniable, but here's where it gets really interesting, and also where I have to push back a bit.
Go for it.
If the system is keeping O of raw tokens around in memory, specifically, so it can reread them later, we are storing a sequence log. Haven't we just reinvented the Transformers KV cache and sacrificed the O of one memory benefit that makes RNNs appealing for long context deployment?
That is the obvious critique, yeah. And that critique highlights why we need to rigorously define the difference between storage memory and working memory.
Okay, break that down.
Yes, retaining the raw tokens means your cold storage is O of T. But the active recurrent state computation, the actual working memory that the model uses to generate the next token, remains fixed at O of 1. It creates this two-level memory hierarchy.
So it's cheap, lossless static storage versus a highly compact, revisable active memory.
Exactly. When a transformer decodes a new token, the attention mechanism is forced to compute an inner product across the entire O of T KV cache.
It's brutally slow.
Right. That computation scales quadratically with sequence length and eats massive amounts of memory bandwidth. In this dynamic recurrent model, decoding a token during the standard forward pass still only requires O of 1 compute against the 111,000 element state.
So you aren't paying the attention tax on every single step.
No, you are only spending extra computational cycles during the targeted rescan phase. And even during that rescan, you are processing a rigidly bounded subset of the history, just 21 tokens, not the entire sequence context.
You maintain constant time generation during the actual output phase while reaping the benefits of high-fidelity historical recall.
Exactly. You trade a localized burst of compute for massive memory savings.
We are trading a highly localized burst of compute during the rescan to save massive amounts of active working memory capacity across the entire generation phase.
Yep.
But there is a massive caveat to the 111K versus 3.1 million result. Those were Oracle results.
Right, the Oracle bound.
The researchers explicitly provided the model with the ground truth labels for where the functions lived in the sequence, so the selection aid knew exactly which index to output.
They gave it the cheat sheet.
Yeah. Real-world natural data doesn't come neatly packaged with bounding boxes and basis identifiers. If this is going to be deployed by ML engineers, it needs to be self-supervised.
And moving from an Oracle dependency to a self-supervised protocol is where this paper transitions from a clever engineering trick to a profound statement on model mechanics.
Because they actually solved the continuous to discrete routing problem.
They did, by repurposing the model's own beta gate. To train this label-free pipeline, they developed what they call a repeat model.
A repeat model.
Yeah, they took the standard training sequence, the basis functions, followed by the few-shot query examples, and instead of asking for the answer immediately, they concatenated the entire sequence of basis functions a second time before the final query.
So they essentially built a distillation pipeline using the model's own gating behavior.
Exactly.
Because on that second pass, the model has already ingested the few-shot examples. It possesses the forward-looking context, so it knows exactly what task is required.
Because the model knows the task, the internal gating mechanics naturally adapt. The researchers monitored the beta gate, the update strength signal during that second pass, and they observed an emergent property.
This is the coolest part of it.
The model naturally spikes its beta writes on the exact tokens that are relevant to the query. It realizes it needs the weights for function 2, so when the tokens for function 2 appear again, the beta gate aggressively opens to write those values into the recurrent state with maximum fidelity.
So it's like watching a panicked student's highlighter strokes when they re-rate a textbook right before an open book exam.
That's a perfect analogy.
Right, because if they already saw the practice test, they aren't highlighting generically. They are aggressively highlighting only the specific matrices and paragraphs that solve the exact queries they know are coming.
Precisely.
And then you use those exact highlighting patterns to teach other students what to look for without human labels.
Yes. To operationalize those internal signals, they took the final layer beta patterns generated over many sequences and applied k-means clustering.
Okay, k-means clustering on the beta pattern.
All right. They were looking for high write strength patterns and found a clear elbow in the clustering at 3 centroids, which mathematically aligns with the k equals 3 distinct functions hidden in the context.
Amazing.
They converted these cluster centroids into a discrete codebook. The codebook consists of fixed rescan choices, specifically sequences of 21 tokens, which maps to the 16 pairs plus the query formatting overhead.
So step 4 is just seamlessly training the dynamic model to predict a code from that unsupervised codebook, completely replacing the oracle.
It just drops the oracle entirely.
The collection head reads the few-shot examples, outputs a code from the codebook, and the system executes the rescan on those specific 21 tokens based entirely on the beta gate patterns it learned to cluster.
And the empirical results of this self-supervised codebook model validate the entire pipeline. It definitively outperforms the single-pass baseline.
Let's talk numbers on that.
For k equals 3, the validation means squared error for the massive 3.1 million parameter single-pass baseline was 67.06.
Okay, 67.06.
The label-free dynamic model, using just the 111,000 element state, dropped that mean squared error down to 4.91.
Driving the MSE from 67 down to under 5 purely by allowing the model's internal gating mechanics to supervise its own rereading strategy. That's incredible.
It's staggering. It approaches the Oracle upper bound, which achieved an MSE of 2.30. It definitively proves that a recurrent network can derive highly accurate supervision for dynamic memory allocation without requiring human-engineered bounding boxes.
It actually learns to manage its own attention and working memory capacity.
Exactly.
So zooming out from synthetic linear functions, what does this mean for the future? The implications for ML engineering and the future architecture of AI models are substantial here.
They really are.
Because continual learning, processing heavily extended contexts over time, is fundamentally a data compression problem.
That's all it is at the end of the day.
And the primary takeaway for engineers is that this paper proves a highly viable new compute memory trade-off. Historically, achieving high performance on complex multitask reasoning in long contexts meant deploying models with massive recurrent states, or just unmanageable KV caches.
And deploying massive states is brutally expensive at inference. What dynamic compression offers is an alternative deployment architecture. Engineers can deploy much smaller state models with memory footprints that comfortably fit on constrained hardware and allow them to dynamically spend extra compute cycles via rescanning at inference time.
You are dynamically recompressing the historical context around the specific, immediate demands of the current task.
Exactly.
Which allows a small state model to punch vastly above its weight class in reasoning benchmarks.
It's highly efficient.
It provides a framework for deploying highly efficient models with dynamic inference capabilities. Now, obviously, we need to address the limits of the current research.
Sure, there are limits.
This was executed in a highly controlled synthetic setting with mathematically distinct matrices. Extending this beta codebook method to natural data pre-training, like causal language modeling, where the structure of tasks is infinitely more chaotic and overlapping, is the immediate next frontier.
Yeah, you cannot simply apply k-means clustering to natural language dependencies with the same mathematical cleanliness as an overdetermined 8x8 matrix.
Right. The open architectural question is how to parameterize and cluster the space of possible rescans in a million-token natural language context, where semantic meaning is distributed, not localized in neat 21-token blocks.
Exactly. That's the big unknown. But the proof of concept that a model can autonomously derive a discrete routing index from its own continuous gating signals changes how we should think about training future architectures.
It completely reframes it. If a model can effectively learn to selectively rewrite its own active working memory based on downstream task demands, what happens when we unleash this dynamic rescanning capability in reinforcement learning post-training? Could an agent eventually learn to autonomously plant its own latent bookmarks throughout a million-token context, inventing entirely alien non-human algorithms for navigating and reconstructing its own memories?